a typical example of a rough spectrum with, in fact, with this second sample put inside the spectrometer 8 days after the electrolysis, we were able to see the peaks. And here we are seeing the peak at 89 keV. This other point clearly is the spectrum, a peak of a thorium, which is not thorium of the surrounding, but is thorium just on the plate, which predictably comes from water-free solution and then deposition on the plate. The half-life of scandium is 84 days. So we were achieving this spectrum for 11 days. After we have a stop for 70 days, and 70 days later, we could observe this spectrum. And so we see that the original one, due to scandium, was decreased, whereas the spectrum of thorium, which is quite stable, was unchanged. This is the rough data after it was automatically cleaned of the background, and we could obtain this table. In other words, the intensity of the peak is about 4 sigma at the beginning. 70 days later, it is reduced at the background level, probably 1 sigma. The story is not finished because we had another reaction to control. That is the reaction of titanium 50 with deuterium, producing scandium 44 and helium 4, which is again beta unstable and decays with 3 gammas. It's a problem to find out where is it. This is. One gamma, 2 gamma, and 3 gammas. This isotope has a much shorter life, and in fact decays in about 42 hours. Data were achieved during that period, and the table, where is the table? Is showing our results. All the peaks were identified by the automatic research system. This was not well shaped. And the number of counts was decreasing by the end of the run, which means that indeed we were observing a metastable species with the time of life at at about 2 days. If eventually we are putting into a graph our results, we see that the number of counts which we have detected for the second species was not far from the steady state concentration, whereas those of the former experiment were well below to the steady state. If both the systems are extrapolated to the steady state conditions, we have that for the reaction deuterium plus titanium 48, we have the metastable species of the steady state concentration, which is about, or steady state production, which is about 1 species at every 30 seconds. And for the other, the longer living, we have a production larger at about 1 species at every 15 seconds. In conclusion, this detected radioactivity cannot surely account for the thermal effect, but it constitutes the fingerprint that the anomalous heat effect must have a nuclear source. I'm finished.
Oh, God.
You said that your electrode gains weight slightly, gains weight. The weight at the end of the experiment is more than at the beginning.
Yes, because my very slight increase. You see, the weight of that electrode was less than 1 gram. To explain the heat observed, which was at least 200,000 or 300,000 kilowatts, it should be totally converted in titanium kilojoules, excuse me. It should be totally converted in oxide, and it was not enough. So I think that the small increase, a few milligrams, can relate with the absorbed hydrogen.
Well, my question is, with this increase in weight, what about the morphology of the electrode? Did it stay in one piece, or was it cracked?
No, it more or less clearly I have not made an investigation on the morphology on foreign species on the electrode. We were focusing on the detection, if any, of a nuclear species.
Okay.
But the appearance more or less is as the beginning, probably a bit darker.
Okay, so it might be a good idea to see what makes it dark.
You did a coincidence measurement, gamma coincidence. Okay, and then my question is, the titanium has a stable isotope of titanium starting from 46 to 50, or 52, maybe small amount now. So why you said you see the only scandium 40 decay of the scandium 46 and 48? Why didn't you see the other isotopes of scandium?
Well, we have. I think that we were needed the cascade, the gamma cascade, that is more than 1 gamma ray to be detected by coincidence.
Yeah, sure.
And probably there is also some other reaction. And in fact, working in coincidence, we were able to see other peaks which were not identified, you know.
You mean the statistics is not enough to identify them?
Pardon?
Statistics. You need more yield. Or
Yes.
Did you look for neutrons during the excess heat production?
I think that your results didn't show effects because you have background about 7 per canal, but effects you have about 11 per canal. It is not statistically enough. You have only one statistic error in your effect.
No.
Yes?
What I have shown. What I have shown.
Shows this
Yes.
transparency.
This one.
No, transparency. This experimental results.
Yes. This was not yet
It's
clean.
gamma.
Yes. This I have told. The experiment were not clean of the background, you know.
It is not statistically enough peaks
Yes,
which
yes.
you indicate.
Yes.
It's less than one error, but you must have 3 errors.
Yes, but you mean this?
Oh, yes. You have background,
After, yes.
7 per canal.
Yes, but this
So-
background
Yes.
is taken out by the reference to
Yes. And your effect in this peak is 11 counters per canal. Yes? And effect is only 4 counters. It is not enough
For me,
when you have statistic errors about
for me,
4.
for me is
Effect
enough.
4 and error 4.
Yes, but for me is enough because through the measurements, this was my result.
This is the same. You have 1000 per canal background, yes? Background is how? What? Your background.
Background.
This region.
This is corrected by the background.
Yeah. Так what is background? What is background is this region? About 1000.
No, this is the energy.
Yeah. And what is background?
This
How
is the
counts? How counts per canal is background? What is background?
background. It's not background.
Where is it?
It's not the background here. This is
It depends from your background. It's
What you're missing is coincidence.
how much counts is counts per canal is your background.
I have to check on the book what is about, but the statistics which we made gave this results. That is the uncertainty about the peak was 7 and 5.
Well, maybe here it's near the effect, but in previous
previous one.
transparency you haven't.
Yes, but I was telling that this, for working, I have to
Just
take
to
out
see
the
it.
background.
Just to see it. Yeah.
I have to take out the background, you know.
Statistics.
And you see also
So per canal.
you see also that when I was making again the measurement 70 days later, the peak was again identified by the automatic system. This peak is practically unchanged. And this
How
is,
much in this peak counts? How much?
This is 10 counts.
10 counts only. And background how much?
Is could be between 4 and
7.
between 4 and 5. Okay.
Yes. And you have effects about 4 or 5, and you the same have error, statistical error.
For,
Yes?
For me, when cleaning out the background, the result was what I have reported, you know.
Okay,
It's just showing them where it is.
Discussion now, and want to have a coffee break now, and please come up here at 11:15.
Got it? Yep. Okay. Jed Rothwell and I have noted that in recent months, the American Physical Society has had what effectively appear as attacks against cold fusion through something that was on the APS News, and indirectly through things that Robert Park has written. In the interest of maintaining a sense of balance, we felt it was appropriate to draft a letter, and I'll read it to you in a minute. And if you're interested, come in contact or contact either Jed or me by email, and if you'd like to sign it. The letter is the following, and we can modify it too in discussions. But in recent months, cold fusion has been attacked in APS publications and in a book published by APS spokesman Robert Park. Because the information contained in these attacks is biased, unscientific, and contradicts material published by the APS and in the peer-reviewed scientific literature, in the interest of maintaining a balanced presentation of the facts, we request that a formal statement be made by the APS apologizing for these distortions and disavowing Dr. Park's comments. So it's just really to make them accountable for what's going on. So just contact us. All right, thank you. Thank you very much.
So the first talk for this section will be given by Professor Scaramuzzi, paper 61. Title my report here is my colleague from Tomsk Technical University. Object of research is a search of new condition of the excess heat in the process of electrolysis, isotope hydrogen separation of metals, namely under excitation condition of hydrogen subsystem metals during electrolysis. Plan my report is following: information about new phenomenon, excitation of the hydrogen subsystems by ionizing radiation. The second part is possibility of citing the hydrogen subsystems during electrolysis, and excess heat under excitation condition of the hydrogen subsystems. Okay, it's some information about new phenomena, excitation of hydrogen subsystems by ionizing radiation. One of the problems we studied in Tomsk, it is effect of ionizing radiation, electrons, X-rays, gamma quanta on heterogeneous metals. We have established ionizing radiation stimulates the intensive diffusion and hydrogen release from metals at room temperature and below it. It is possible to see on this figure electron effect on the sample. Sample cooled by cold water or liquid nitrogen, and in any case we observe intensively release, in this case deuterium release, and hydrogen doesn't matter. I mean, situation say that sample have energy of room temperature, but hydrogen have much higher energy in process irradiation. Second, experimental facts. It is rate of hydrogen release grows superlinearly with hydrogen concentration and electron beam current density. It is for stainless steel and niobium in this case. In this result shown that behavior hydrogen observed collective process. Third experimental results, it is local effect of the electron beams stimulated hydrogen release from all samples. For example, if you effect on palladium, size about 2 multiplied to centimeter size, beam of electron about 1 to millimeter, and it's in room temperature, we put this sample, hydrogen, the deuterium released from all this bulk. It is tested that hydrogen atom connected with each other and provide the energy interchange. Okay, that's important result too. It's important so during the effect electrons the sample, for example, palladium-2, hydrogen release or deuterium release not only molecular form but atomic form too. Now if you have a special pigment which change color when it interacts with only atomic hydrogen, but not molecular form, and don't change color during the irradiation. It's possible to see. It's a real situation that hydrogen release bulk during the effect atomic form. Okay, experimental result tested first. Hydrogen atoms occupy regular position in crystal lattice, form their own hydrogen subsystems. In these subsystems, hydrogen atoms are connected with each other much stronger than this atomic matrix. The hydrogen subsystems is able to accumulate the external energy, for example, radiation energy. Frequency of hydrogen subsystems oscillation lies beyond the phonon spectrum of crystal. Therefore, the energy absorbed is distributed inside the hydrogen subsystems for the first instance, and hydrogen atom energy is much higher compared with energy room temperature. So, hydrogen substance in metal is reality, and it can be excited by external effect. Next stage of research, our research, we try to understand it's possible excited these hydrogen subsystems during the electrolysis process. I'm talking now about second part of my report. It's investigation of the excitation hydrogen subsystems during electrolysis processes. The excitation of the oscillatory degrees of freedom of the hydrogen subsystems during the electrolysis processes may initiate break of gas cavities, cracking of electrodes, electrolyte turbulence motion, and other processes in electrodes and electrolyte. The excitation of the oscillation in the hydrogen subsystem in first approximation, it's possible to consider like force oscillation caused in liquid or gas by the variable external effect. Let hydrogen subsystems have own resonance frequency omega 0, then oscillation, excited process of breaking gas cavities or cracking of metals with frequency of omega close to omega 0 will amplify the oscillation amplitude of the hydrogen subsystems. Oscillation initiated by the gas cavities break and metal cracking lay in the band of ultrasonic frequency. Therefore, if excitation of the hydrogen subsystem takes place, its own oscillation frequency will be situated in the same band. To detect such oscillation more effectively, it is piezo sensor used. In order to amplify the process of the hydrogen substance excitation, source of the excitation, gas cavities, were approached to cathode by means porous electric tubes fixed near the cathode, like shown on this figure. It is acoustic signal sensor, and around the electric field. Experimental set in construction of measured cell was shown on this figure. It is cell, it is cathode, around it dielectric films, and sensor, and program which looks what's happened during this process of electrolysis. At the first stage of our investigation, we have to examine whether acoustic signals emitted upon gas cavities break are different from the ones emitted by heterogeneous metals. To solve these problems, we choose metals for research. It is aluminium, not absorbing hydrogen, stainless steel, absorbing hydrogen moderately, and titanium, absorbing hydrogen very well. On this figure show amplitude spectrum, acoustic emission in process of deuterium loading of stainless steel, titanium, and aluminium. You can look metal which absorb very well, energy and intensity rate of acoustic signal much higher compared with aluminium. Another test that we detect normally break gas cavities, it was following. We measure we have examined acoustic emission release for stainless steel in two modes. First case, stainless steel was cathode. The second was stainless steel anode. When stainless steel cathode, acoustic emission much higher and much higher energy too. Green curves show when stainless steel was anode. Okay. First and second experimental results shown that acoustic emission gives information about process occurring in metals and initiated by hydrogen. Next stage, we try to look what happened. Yield of acoustic emission depends on density of current electrolysis. In order to amplify excitation effects of hydrogen subsystems, the sample titanium and stainless steel can be preliminarily saturated by hydrogen up to maximum concentration. That for every current density used new sample and measure such function, yield function, current density. For iron, which don't absorb hydrogen, we look linear dependence function. Is for stainless steel titanium much stronger differ from a linear dependence. Such dependence usually such behavior of curves tested is the display of collective processes of the hydrogen systems. We also measure voltage cathode anode, and investigators show that with increasing current density, variable component cathode anode voltage increases. Upon certain G, cathode anode voltage change occur according to periodical law. Voltage pulses present this composition even in details. There is some correlation between rate of acoustic emission release and voltage pulses. Okay, when we believe, after that experimental result, we start to believe that it's possible to excite it, hydrogen subsystem, and during the electrolysis process, and decided to look what's happened with heat release. For this purpose, we used sample stainless steel and titanium dimension 1 multiplied 30 mm square. Metal has been covered by porous lapsam tin with thickness 8-10 micrometer. Between film and metal, there was a gap which allowed the electrolyte solution to freely circulate along the metal surface. Palladium was used as anode. Heat release was measured by flow calorimeter and electronic devices like that. It is simple flow calorimeter system which measure flow, rate flow, and temperature, and current, voltage, cathode anode, because voltage cathode anode change during the electrolysis, we measure voltage in 0.01 second. And after that, we calculate input power. As mechanical properties of the film is not well, before measuring heat release, samples were saturated by deuterium in condition in high current density during the 20 hours. Result of measurement I will show now. Okay, this ratio output power to input power. When we used heavy water and light water for titanium metal, more than red curves, it is light water without film. This curves light water with organic film. This difference is about 6-7%. If you look saturation when we used heavy water, situation same. Green curves, it is without films and with organic films. This difference is about for titanium 20%. Results very good reproduced. It's practically every time we look such differences. Now I would like to show excess heat increase with current density. Current density, first curve, it is measurement, our measurement. The critical current density when appear effect is about 0.5 ampere centimeter square. Second curves, two curves, it is curves we take from word Sturms, from review. Sturms, it's similar dependence to. Release heat depends very strong of size of holes. It's possible to look here. We have not very small holes. In our case, finished about 0.45 macro meter. Sorry. Okay, it's enough. Heat release increases temperature of the electrolyte and saturates at 40-45 degrees centigrade. And I would like to show you what's happened with cathode, titanium cathode, macro photograph of titanium 30s, hydrogen during 2 hours at current density 1 ampere centimeter square. You look holes, round holes, different size, and observe some cracks too. Okay. Our research will show show if together with research effect of ionizing radiation in metals during the saturation hydrogen appear hydrogen subsystems. The hydrogen subsystem is able to accumulate external energy, for example, radiation energy. We suppose that it's possible accumulate energy during the electrolysis effect. Frequency of hydrogen systems oscillation lie beyond the phonon spectrum of crystal, therefore the energy absorbed is distributed inside the hydrogen subsystem. And hydrogen, in this case, have much higher energy compared with energy room temperature. And we stable, we observe release heat more with dielectric films compared with without dielectric films. Thank you very much.
I'm curious about the nature and of this organic film. Can you tell us what it is and how you applied it? And did you see excess energy in the absence of such a film?
I should say, really, we measure relatively release power, release heat without films, with films. Now we finish prepare calorimeter like Makubri calorimeter, and we only start measure. First measurement was shown that we observe excess heat. But what which I discussed, it is connected with relatives. Measurement with film and without film.
Well, what kind of film is it? How?
Okay. It is organic film. It is a nuclear filter. You know, nuclear filter. I mean, whole produced by heavy ions. You know about it?
Nuclear pore. Yes.
It is special filter now doing in the United States too and Russia too. And during the heavy ion make small hole in the filter, and we use such holes.
It's a micropore. It's cortex.
Cortex?
No, it's called nucleopore.
Could you tell me the
It's a
frequency
plastic
range
film
of these
made
acoustic
with
detectors?
charges that go
And
through
did you
and
do
etched.
Fourier analysis to see if there's any certain resonance frequencies occurring?
Our acoustic sensor, it is 20 kilohertz, 20 kilohertz. But maybe it is not best sensor. We now try to use 1 million and so on. It's necessary to look what's happened if you measure another diapason frequency.
Joseph Gruber. In your diagram on the development of excess energy, excess heat, you showed only the development up to 2000 seconds, 33 minutes.
Okay.
Did you also make experiments for a longer time, and what are the results?
which we now have dielectric organic films is destroyed during the 2 hours. We have a result during only 2 hours. As we before measured, we during the 20 hours saturate hydrogen, the deuterium material, to get this effect. Before, we don't, if put here, we don't look effects.
Is there more questions? Okay.
That's yours.
Next talk will be given by Dr. Sharp, paper 25.
Yeah. Our theory really hasn't changed very much over the years, although we have not. The title of the talk is Theoretical Framework for Anomalous Heat and Helium-4 and Transition Metal Systems. This work I've been doing on with Talbot Chubb. An important point, though, is that what we have not done in the past is to really focus upon elements associated with the reaction theory of it. We've given sort of intuitive descriptions that actually relate to an important point that Julian Schwinger brought out at the first annual Cold Fusion Conference, the point being that in the kinds of environments we're talking about, the nuclear and electromagnetic interactions should really not be treated as behaving on very different time scales. They shouldn't be treated as being separable. And this kind of thing can occur through coherent processes. That's what I'm going to be focusing on. I'm going to start by looking at the problem, the obstacles to be overcome in getting outside the box, and then the motivational physics for getting outside the box. And this involves how we can actually describe things associated with coherent processes and how they relate to what we know about conventional nuclear physics. And then I'm going to talk about some more exact physics that relates to this motivational physics. The motivational physics describes the coherent processes, which are well known in solid-state physics, but it's a different limit than people are usually used to thinking about. Then I'm going to talk briefly about the ion band state theory in its generalized form, where we now incorporate the presence of nuclear wave functions based on realistic nuclear potentials and how this relates to the reaction theory problem. Then Talbot is going to talk about ways of looking at these ion band states and why they are actually sort of counterintuitive, but actually there is important information based on measurements by Puska and Staldy and a number of people involving these kinds of systems that these things actually occur. Now, what I mean by the box is, on one side, we have what we know, conventional physics, inside the box. What we suspect might be true, or might be unconventional. Bob Park calls it voodoo. I don't. Anyhow, just take that as a term. The point is that I'm going to argue that, well, I'll show it in a minute. I'll talk about first inside the box. When we're inside the box, I've depicted here the conventional nuclear reactions that one sees. The blue is a neutron, the red is a proton. Characteristic length scales of Fermi's and momenta 10 to the 9th eV per scene. This is a deuteron. A deuteron comes together, forms an excited state of helium-4, which should be viewed as an excited state of helium-4. When nuclear interactions are separable, that is, of very different time scales, you can ignore the electromagnetic process, the effects of the electromagnetic process on the behavior of the nucleons. And essentially what you get is a symmetric kind of series of interactions where you get helium-3 going off with a neutron and tritium with a proton. However, there is, of course, this reaction which I've deliberately shown being close to the edge of the box, where the actual interactions are not separable and should not be treated as separable. And in fact, this is a very important point that also Peter Hagelstein has now brought into his theory too. Now what I'm going to say is that, in fact, I'm going to raise the important point that being inside box means we are outside the solid. So here I've depicted these same reactions, and now I'm talking about the solid. Here we have 10 to the 9th electron volt per c incident momentum, and in a solid, the characteristic incident momenta are like 10 to the 4th eV per c, and it's conventionally thought to be virtually impossible for the nuclear and atomic scales to talk to each other. However, the electromagnetic interaction penetrates to all length scales, and it can, in principle, make this coupling possible. Now, what I'm going to argue is that through the known wave properties of solid-state physics, the non-local wave properties of solid-state physics, which can occur coherently, this can be made to happen. And in fact, the existence of coherence is implicit in everything that solid-state physicists do. They don't normally emphasize this point, but it's there. And there's been some confusion about this, even in discussions at this meeting. This notion of coherence is very closely related to some of the things that Emilio Del Guidici mentioned. However, his coherence is actually occurring at a very different temperature scale and has very different characteristics than what we are describing. Doesn't mean that the two can't be related, but in terms of the most dominant effects, there are other things that happen. Now, I'm going to focus for a minute and then get back to the problem. We consider a situation with P, the momentum, equal to 0. This is a very funny configuration. P is a non-physical quantity. People don't remember this. H over lambda is based upon what is called the canonical momentum. It's not mass times velocity. There's another non-physical variable in the theory called the vector potential. The point is, a combination of these two quantities, this is associated with the wave function of a photon. This is related to the current, and I'll show the equation for that in a minute. But the point is, P equal to 0 corresponds to a situation where the wavelength, the de Broglie wavelength of the configuration approaches infinity. Now, this normally doesn't mean, in free space where there are no boundaries, this means nothing and it's not very overly important. When there are boundaries, it becomes very important. Now, the point is, as I said, the uncertainty relationship momentum, P, also called the canonical momentum, is not mass times velocity, which can be, as a density, can be written as mass over charge, mass of a particle over charge, associated with the current of the charged particles. But this quantity is, one can think of it as P minus E over CA. We all know this, but we tend to forget it, because normally A isn't all that important. Solid-state physicists like to get rid of A by introducing boundary conditions. Now, the point is, and this gets back to some of the things that Emilio was talking about in terms of just general coherence. In a general many-body framework, this can be written as the expectation value of a quantity, h bar E over m, times the gradient of the phase, the same phase that he was talking about, the phase of the many-body wave function. That is a situation where you have a number of different particles in lockstep with a common phase. And then it's minus E squared over MC over A. Now, in most situations, you don't get coherence, but you can in this peculiar situation that I've depicted here. The P going to 0 limit is 1. There are others that I'll talk about in a second. In this kind of situation, what you get, when P is equal to 0, this expression says that the current is proportional to the vector potential, but because the vector potential is derived from an integral of the current, you get a constant current, a constant vector potential. A constant vector potential creates a constant current, which creates a constant vector potential. That is called superconductivity. Now, there's another thing that is required because of the presence of the boundary that makes all of this meaningful. The presence of the boundary gives you a way of monitoring what's going on. At the presence of the boundary, the current vanishes, which means that when you integrate the current around the loop, around the boundary, you have to get, because the wave function, the overall wave function, must be well-defined. It must be single valued. Its phase can only change by 2 pi. That gives you what's called the Meissner effect. So that is really the motivating physics of what is called gauge symmetry, or broken gauge symmetry. And leads to a lot of interesting things. Gauge and non-local quantum mechanics. P does not have to be a local quantity. Near zero energy and near zero momentum, confusion has existed. Zero really does mean zero. When there are boundaries there, it is not zero. When there are boundaries, you have to consider what goes on. Charged particles can be near each other without high velocity. The current can be small, but the momentum associated with the canonical momentum can be large, but compensated by something happening with the vector potential. And what that leads to is the possibility of non-local momentum release. Charged particles are always closed with photons. What that means is mass times velocity is E over c times photon wave function. The Bohr condition is actually intimately related to this. Mills has misrepresented this. P can change discontinuously. If you take anything away from anything that I say, P can change discontinuously in a non-local way. When this happens, particles can come close to each other, in quotes, because the current is physically measurable, while separately neither P or E over C can be measured directly, especially near zero. P can change discontinuously through these effects. So boundary conditions are important, and solid-state physicists use this all the time. The requirements of broken gauge symmetry, why it is usually unimportant, are appreciable numbers of particles must share or approximately share a common phase, requires that interaction timescales be appropriate. There have to be finite excitation gaps, or things that make this possible. Boundaries are necessary. Certain regions of space are forbidden. Examples of broken gauge symmetry in solids, as I said, the Meissner effect, well known. Spontaneous lattice recoil, as in the Mossbauer effect, can be attributed to not actually from the situation where you have zero momentum, but you have a periodic lattice, for example, and then what happens is you can get changes in momentum, discontinuous changes in momentum, large ones. It is an example, mathematically, of broken gauge symmetry. Umlauf processes, which are the basis of describing thermal conductivity in solids, were identified in the 30s by Parkes. Same thing, broken gauge symmetry. Very important, though, in terms of what I'm going to be saying. Broken gauge symmetry only has to be approximate, and in fact, in the motivating equations I'm going to describe, it's when there is some form of something reminiscent of gauge symmetry, or the breaking of it, that one can talk about coherent processes. All right. To understand how this comes about, I've sketched what is well known, actually, in terms of reaction theory. Here I've denoted an exact wave function. This is exact. This is the exact perturbing potential associated between a final state and an exact initial state. The rate expression in its exact form for arbitrary strengths of potential is very similar to a Fermi-Golden rule type of expression. The point is that is new in writing this, as opposed to the more proximate ways we've discussed it in the past, is the potentials are arbitrary. But because they're arbitrary, it's almost useless. This is a many-body potential. This is the thing that that Dr. Kim sort of alluded to, except this can include, in principle, everything, all of the charged particles that are around. Now that, one might think, becomes a meaningless problem. However, there is a well-established technique for identifying the forms of interaction, and actually that can be used in a quantifiable way when, for gaining progress in this reaction rate expression, provided some knowledge of the exact wave function can be inferred. The point is, normally, well, the way that one does this is by actually going back to the Schrodinger equation and recasting the potential that sits in here with a kinetic energy operator and introducing non-local physics. This goes generically under the title of multiple scattering theory, or Karinga-Cohn-Rothstocker method, or, you know, there are a number of different ways of talking about it. But the point is, we know this. People do know this. It's actually been used for many years. People haven't thought of it in the context of this problem because people have been focusing on the idea that the reaction has to be local. In other words, one starts with a kinetic energy operator to replace the formal representation of the many-body V, many-body potential that sits in here. There's actually I think there's a sign mistake in here, but it doesn't matter. If you take T here, refers to the sum of all of the Laplacians times h bar squared over 2n that one normally thinks of in the problem. The point is that energy minus T is the potential associated with this psi. Energy minus T acting on here is the potential associated with this energy, with that state. And when one takes the difference between the two. One gets back the potential that sits in here, and then one integrates. I'm just going to use my pen. This is a many-body integration, and the key point is that because it's evaluated at energy equal to energy prime, you're just left with the kinetic energy operators, and what one can do then is literally integrate by parts, apply Green's theorem, but the point is that in a many-body situation, there are locations where the potential V becomes singular. That is, it can go to infinity, such as at the traditional points where charged nucleons can overlap. And at these points, there are two possible situations. The, in quotes, gradient can become infinite, or it simply can become discontinuous. And to be well posed, if the reaction rate is to remain finite, rather than become infinite, what happens is you get the possibility of discontinuous behavior in these gradients. The gradient of the wave function, I'll have you recall, is the momentum, so that when this happens, you're simply getting a discrete change of momentum, and it's non-local in character. Okay, and pictorially this can be represented in the following way. What happens is when one looks at all the different points that are around, there are momenta associated with it, one has to sum over all of these locations where these singularities occur. One gets differences in momenta, and you have an overall center of mass momenta of the entire solid. The overall solid can recoil in this, as opposed to the situation in which Peter Hagelstein was describing, where it doesn't happen. But when that happens, it collides with a boundary up here, and you get the transfer of momentum up here. And so, in particular situations, for example, at low temperatures, you get what in quotes might be viewed sort of as a bulk effect in which the entire solid moves up, hits a boundary, and you get results associated with it. At higher temperatures, the idealization of the perfect solid begins to break down, and you get things in isolated clusters. Okay. Now, final point about this is regarding two things. How does coherence enter? Well, coherence enters because when you start with a reaction rate expression, which I'll remind you is very similar to a Fermi-Golden rule, all of the expressions of reaction rate start from this expression. Things involving Gamow factors and so forth, they really start from this expression. But they make approximations. When you take this expression and you move it, and you have a situation that applies in a solid. In a solid, you have a thing called periodic order. That's the next step up from momentum equal to 0. When you have periodic order, you have the following interesting phenomenon. You can have sudden changes of momentum. These are what constitute things like Umklapp processes and the things that I talked about. The momentum, k plus g, can change discontinuously and become k on any time scale. Now, and that's due to the non-local effects. Now, this is related. This can be related back. One can actually derive what the reciprocal lattice vectors are from this kind of thing. Closed loop here, though, it's just referring to an integral from one place of periodic order to another. The point is that when one has perfect degeneracy like this, there is an inherent phase. The things are coherent. They are marching in lockstep. When you change one, you change all the others. Because the phase changes in the same way. And what can happen then is because n times E is equal to the total energy, you can take the delta function, pull out a factor of 1 over n, because delta of n times E is equal to 1 over n times the delta function. That gives you the n over here. These things in general, when they're non-coherent, could add destructively, and you could get 0, and you don't know what the answer might be. So in many cases, that's not correct. But when it's entirely coherent, this integral, which is a many-body integral extending over everything, can be related to the integral to n times the integral over a single unit cell. The key point is that the whole thing is required to maintain periodic order in that limit. However, the thing that's just a generalization to illustrate the importance of degeneracy. The expression is perfectly general. You can take this and move it around. You can make it coherent in some places and not in others, and one can actually have hope of modeling this thing. The final thing of interest is the limit in which the rate actually is entirely 0. That corresponds to a situation in which one can identify and calculate the meaningful eigenstates in the problem. And that actually falls generically, oh God, 5 minutes left. Well, I don't have much time. I won't bother with talking about the rest of this. If you're interested, there is a formulation It's based on standard many-body physics and band state theory. If you want to talk about it, you can talk. We'll just talk a little bit about the nature of the wave function and what happens in our ion band state theory.
Okay, we end up with two-body wave functions to describe the pairings of n times n-1 deuterons in a coherent state that is partitioned by into many potential wells by the lattice. And I just want to illustrate what the feedstock, the deuteron two-body wave function looks like. It's a six-dimensional wave function. We're concerned with basically 3 dimensions in physical space, giving the charge density in the sites in the lattice. And then there's the internal interaction, which is described by 3 dimensions of internal space. In this picture, we have the singularity associated with the nuclei distributed over n-cell unit cells, and these point singularities give you a cusp in this separation space. When the reaction occurs, this reaction doesn't really change the distribution in physical space, but the deuterons in separation space are limited to the nuclear radius of the product. And just the final overall summary picture or the statements are for this theory is that in general we see that fusion without high energy particles requires partitioned, overlapping wave-like deuterium matter in a crystalline lattice for the deuteride type of cold fusion, and that there are potentially large changes in momentum which occur because the correlation wave function, which we call GR12, is a potential that includes matched electrostatic and nuclear components, and that de-excitation occurs through global non-local momentum transfers to an embedding dissipated medium, which may be the Fermi sea of electrons or the collection of phonon modes in the solid. So basically that's how it's kind of reduced.
I just wanted to point out that these locations where he's drawn the cusps, these points of singularity, these are the points where these are boundaries. These are what I call boundaries in my view graph. Do you have the microphone? Oh yeah. And what he's saying, I mean, what happens is in the rate expressions, one can start with that rate expression that I was talking about, and in order to get a reaction, what has to happen is the reaction rate has to be comparable to atomic scale processes. And that can be done through the coherent process that I was talking about. So, and there actually is a well-defined formulation in many-body physics standard for doing this. What happens is you calculate what is effectively a collision interval from a many-body expression and relate it back to the notion that in a semi-classical limit, you can talk about trajectories and changes in wave vector involving the entities that are present. So it can all be related back. It's standard solid-state physics.
Okay. Yeah, Wednesday. Yeah. Yeah.
I have a couple of simple questions for clarifications.
Yeah.
We know that phonons in solid, they give phonon bands.
Right.
In fact, in Umclav processing invented by fire,
right.
The context of phonons.
Right.
So the phonon excitations are there, and thermal converting to phonons and all are there. Now, in what manner your ion band differs from a phonon band? Because phonon also have this precipitation dielectric.
Yes. Yes. Very good question. The phonons don't have to be treated as being equivalent particles in the sense that, let's see.
Phonons are both particles?
Well, they can, yes, they are. They're treated as bosons. All right, the biggest distinction is that the ion band states are not, they have all anharmonicity built into them. There is no, and they have charge. Phonons don't have charge. The ion band states have charge.
Okay.
Okay? That's the biggest distinction. And they have spin.
Phonons have spin.
Phonons have spin, yes. That's the biggest distinction. And they apply to arbitrary potentials as well. And they've been observed also.
Also, there are other things which don't follow. One thing nobody is talking. There is vibrational mode inside the nucleus.
Yes.
So if helium gets excited,
right.
The protons and neutrons inside the nucleus, they can also vibrate.
Right.
So why can't you?
Well, what I didn't get a chance to show it.
Excited nuclear vibrational.
Right. I didn't show it, but the idea one can do this. What happens is we have made the nuclear and electromagnetic wave functions now non-separable. And what we do, the construct is to take a well-known theory associated with band theory, where they had what they called, in quotes, a muffin tin potential, an atomic region potential. Well, we replace it with a nuclear one, a nuclear region. So it's a much smaller kind of configuration, and what one ends up with in this kind of scenario is a non-separable reaction. One calculates a wave function based on this construct, and one then does the overlap of this wave function with a second wave function, and one can sum over things and include all the excitations that you're talking about. So you're absolutely right. It's very important and should be.
Scott, your theory proposes to solve, or describe rather, two of the problems that we have in cold fusion. One of them is how the nuclear energy is coupled to the lattice, and how this can be done in the short time span of a nuclear interaction. Now, I think you can make a case that this energy can be dumped into the lattice, and there's perhaps examples of that in the Mostar effect. What I want to know is, do you have any examples in the real world of these processes happening at the speed of a nuclear release of energy? In other words, you say that it's instantaneous, but do you have any proof of that?
Well, the idealization, I mean, divorcing from the nuclear part of it, when you get down to the notion of a superconductor, you touch it one place it responds instantly, beyond light distances elsewhere.
But has that been measured? The speed of transmission in a superconductor?
Effectively, it has. You can infer it that way. Yes.
Well, infer, but I mean, has it?
No, it hasn't. Well, I mean, they haven't called it the measure of it, but the spontaneous emission of a magnetic field, the expulsion of a magnetic field over macroscopic distances, the times associated with that are known, and so it is. Yes, that's a real effect. I mean, that's the coherence. That's right, yes.
Stop superluminary processes. Superluminary processes.
Yeah. But I mean, part of the problem here is that people have been thinking in a local way. And it really gets down to, you know, here's the other way, okay? What happens in a Bose condensate? The wavelength is infinite. You can't tell where the thing is. In other words, P going to zero, momentum going to zero is a very special state, non-local. So what happens on the boundaries affects everything. Instant. Because the reason that happens is there's a finite excitation gap required to do the energy transfer that you're talking about. If you don't exceed that excitation gap, then the thing responds rigidly.
My question is with respect to Focardi's talk here.
Yes, Focardi's talk.
Focardi had these beautiful results at 700 K temperature, very high energy production, continuous energy production, showing so at higher temperatures you get better. Now, I would have expected with the coherence and mass power, you get higher again at lower temperatures.
That's correct.
So is Focardi, to your opinion, Focardi's result not going into the direction what we were saying many years ago, that a Maxwell distribution question?
Right. Yeah, I think, you see, the rate expressions, the general rate expressions are very complicated. And once you start exciting things, all sorts of things happen. And what you're saying is really quite true. You start going into Maxwellian, yeah, absolutely. And you know, I think it's important if I leave something here with you, it's the fact that momentum is, I think, the fundamental variable, not energy. And momentum can be non-local in character, but that it's complicated. It's a complicated process, and things have to be done in a many-body framework. And we've had some beautiful ideas by Lee and Kim and Hagelstein. They all fit in different pieces to this problem. It's a big problem, you know, and we shouldn't be fighting about it. It actually is the same problem. It's just complicated.
More questions? Okay, thank you. Next talk will be given by Professor Cosima, paper 46.
Professor Cosima's got a good theory too.
Okay, thank you.
Good evening. Fine day outside. In the room with cold fusion discussions. Presentation today is DMCF model of phenomenological approach, of course, to cold fusion phenomenon. I have only 20 minutes and have to give you a phenomenological explanation of the DMCF model in 20 minutes. First, first, I would like to define terminology. Sometimes cold fusion is considered a bad name for this phenomenon we are discussing now. But I'd rather propose you use cold fusion because it is first attacked as a nonsense or mad science. But now, after 10 or 11 years after the discovery in 1989, nobody denies the existence of this anomalous phenomenon in solids with high-density hydrogen isotopes in natural conditions, I mean room temperature, near room temperature. And but there are characteristics not common to the usual science. The phenomenon occurs with qualitative reproducibility with sporadic occurrence. So someone denies to treat this phenomenon as a science and confuses it with UFO or supernatural phenomenon. But we know there are big differences. We can arrange the experimental condition and get, rather say, qualitative reproducibility, but not the irreproducibility. So this is the science with a chaotic character. But I would like to point out one important thing to investigate this phenomenon. Motivation is a mixture of facts and desire. And we from the first stage of this research in the cold fusion phenomenon, there are desire to explain phenomenon with DD reaction. And in my opinion, desire generally spoils the scientific logic. And in the planning, measurement, and analysis, and so on, are biased by our desire. So my talk will be biased by my desire. From my aesthetical point of view, I want to explain the cold fusion phenomenon with 4 events in the cold fusion phenomenon by one theory. Perhaps it is a bold requirement and should be supplemented by other approaches. But now, today, I confine my talk, my model is the best one, not necessarily any others. Sorry, Charlie and other Einstein and other people. Not assuming your assumptions in my talk. The PNCF model I give you today is a model proposed in the ICCF-8 in Maui and published in Transactions of Fusion Technology, this volume and page. After 1994, almost 7 years elapsed. And in this area, I have made many calculations on my model. And in 1998, I have written a book, this book, only $50 you can buy through Martin Company. Shortage of my time. I have to recommend you to read this book. And on the recent papers, I like to list here. This paper treats neutron spectrum measured by Torino group, giving neutrons up to 10 million electron volts. So it is impossible to explain this experimental result by DD reaction. So there are definitely other reactions causing cold fusion phenomena. This paper treats nuclear reactions in solids according to our model. This paper treats experimental results obtained in Texas A&M universities in 5 or 6 years after the discovery of this phenomenon by Fleischmann, Franz, and Hawkins. And there are other 2 papers following this paper. And the last one is just appeared in the recent cold fusion technology, which is one step from model to a theory. I'd like to explain the nature of model later. because the cold fusion phenomenon is very complicated phenomenon. But I'd rather call it phenomenon, not phenomena, because it's my point of view. It is possible to explain by a theory. And my model is one step to the final theory. And CFP, let me use abbreviation. CFP is a chaotic phenomenon occurring in complex systems at standard conditions with background radiations. Especially, I include background radiation, background neutron. Why? As you know, in 1989, DOE of USA checked rigorously the reality of the cold fusion, but they couldn't show it is possible to occur, and they denied. And in United States and in Japan, many physicists laughed at us. But we laughed at them. Why they are so blind not to look at these facts? So it is very complex phenomenon. So methodology is very important. We have to look at these facts. There are very many materials responsible to the phenomenon. And it is almost confirmed. Necessary condition is inclusion of deuterium, hydrogen, or using a catalyst, lithium, sodium, potassium, rubidium, like that. And the observed quantities are gamma energy, neutron energy, nuclear transformed product. Especially, I'd like to point out position of the elements observed. They are usually in the boundary region. Why boundary region? To explain this character and the sporadic occurrence and qualitative reproducibility. It's the three necessary conditions for the theory to be proposed. And there are also indirect evidence for the nuclear reaction in solid. Heat, helium in the gas, tritium in the gas, nuclear transmutation outside or not determined its position, X-ray, and others. So I had used already almost all my time, but it is fair to point out one point. Methodology. There are, in my opinion, 3 points of view. One is it should be used to explain the cold fusion phenomenon, neutral particles. And other phonon school use it occurs in the solid. So phonon is working as a decisive actor, and others not confined to these, but use deformed form of quantum mechanics or deformed form of interaction like that. And in the notorious book by Gary Thomas,
he did. I was there. Right. He did. Yes. He did.
There are mentioned what Edward Teller told in the first stage of cold fusion research. He said, according to this book, it should be, I don't believe it occurs, but it is real. It should be catalyzed by unknown neutral party. There is a sentence in this notorious. I proposed 1993 some neutron model according to the experiment without background neutron. There are no effects at all. And 1998, Jesse Fisher proposed a new extension of our model, polyneutron. And suggested by this model, I expanded my model to neutron drop, which is appeared May this year in the fusion technology. I have no time to explain the nature of cold model. You can consult with my book. Finally, I'd like to show you interesting figure. This is data showing inverse correlation of solar activity and neutron flux. As you know well, solar activity has a 11-year cycle. This cycle is very accurate, and activity plotted here has a very good correlation with neutron flux. And interesting point is R maximum. R is Wolf's index. It means solar activity is expressed by R. If R is maximum, we have a neutron flux minimum. And the year of recent maximum is 1989. So many experiments done in 1989 conducted by or associated with the DOE program failed because of the lack of background neutron from my point of view. And our minimum in recent years, 1986, 1996. Perhaps main results obtained by Fleischmann von the Hockey were done after around 1986 to 1989, and got good results. And if you did experiment 1996, you got a good result. But the recent result will be not so good, in my opinion. Thank you for your attention. I spent too many time. Thank you.
I will say you that as a model you may look for as the neutral particles model in the first group, not the third group as other, because You say, you understand, yes? It's very interesting about correlation with solar activity. The same is for other models correlation. And my question is, why you explain that neutron trapped in solid matter with energy about some electron volts didn't decay? Why? How you explain it?
I have to explain it by the nature of a model. It is better to consider Bohr model of hydrogen atom. The stationary state assumed by Bohr is contradicting with the classical electromagnetic theory. It should be unstable, but he assumed stability of the orbit and could explain many things. And after 13 years, quantum mechanics was appeared to be a theory. So it is necessary to have an assumption, not explicable by the present theory. My trapped neutron, the stability is assumption, but now after the proposition of neutron drop, it is perhaps correlated with the formation of neutron drop and the stability of trapped neutron. Theoretically, one step is took to the science of neutrons in surface. Okay.
May I ask you why you haven't introduced people about the school of theoretician that study confusion, the coherence school, study confusion?
It's included in the others. Others. Yes.
Now, as I recall, you had neutron bands at one point. Do you still have neutron bands? You worked with neutron bands.
Neutron band, yes.
Yes. Well, band states do have coherence. At temperature equals to 0, they do.
Yes.
So you do have coherence.
Yes.
I also might suggest that the last category, solid state nuclear physics, is many body physics, just a point of language, many body physics with a non-separable electromagnetic nuclear potential.
Yeah.
And what I presented in the last talk actually falls in that line. Okay. Thanks.
I'm making oversimplification.
Yes.
Yeah.
Right.
Could you clarify your comment about the neutron flux from solar flares and so on? It seems if the neutron flux is really important, there are simple experiments that could be done using neutrons from reactors and so on, much higher fluxes. And such experiments, I think, have been attempted. Nothing has been observed. But are you saying that with a long trap lifetime, it would seem that what you want to do is accumulate neutrons? I don't understand this at all.
Excuse me, what is the point of your question?
Why haven't you done an experiment on neutron flux?
Oh yeah, that is the same question, fundamentally the same question as Bajikov. It is assumption in my model. Model have to have assumption, and it is just assumed. And if it is variable to explain many data, as I did there are more than 50 experimental data analyzed by our model, written in my book. This is a palladium, deuterium, lithium system, and the others palladium, not palladium, hydrogen system. Very many data are consistently explained. So I think the stability of neutron is supported by those many experimental data. The next step should be, what is the physical reason that neutron is so much? For instance, neutron density assumed in my model is 10 to 8 to 10 to 12 per cubic centimeter. Many people say, why so many neutrons in the solid? Why so neutrons not unstable? But it is an assumption, parameter, adjustable parameter in my model. And if the model is very valuable, applicable to many facts, the model should be explained from first principle. One step is the neutron drop. Okay.
Next question.
What is the lifetime of neutrons in a metal lattice? And is there a method of measuring the number of trapped neutrons in a metal lattice?
The fundamental assumption is infinite. Lifetime is infinite. But neutron drop, by my calculation, becomes stable with some conditions. But it is a black liquid drop model calculation, so it should be elaborated more fine.
Thank you. Okay, thank you. For introducing the next talk, which will be given by Professor Martin Fleshman, just let me make a couple of short announcements. First, the group pictures are ready and are available at the conference desk, where you can buy them at 10,000 Italian lire each. Second short announcement that Professor Fleshman asked me to add a few words at the end of his talk, so please not leave room.
Well, ladies and gentlemen, this talk originally was supposed to last 35 minutes. It's now supposed to last 20 minutes, and we are late. So something has to give. I think it's, I'll only be able to cover part of the material, and I recommend you to read the paper. The motivation for this talk really was twofold. One is that the experiments on cold fusion are still very irreproducible for a whole variety of reasons. And therefore, if we want to interpret experiments, we should really use case studies. It's a mistake to try and have a idea fix about the interpretation and try and use the same methodology all the time. The second motivation, which is very related to the first, is that we now have publication from NHE used in Japan saying that they couldn't see anything at all. So really, those of us who instigated this research have a responsibility to try and see whether the assertion made by our Japanese colleagues is correct or incorrect, and if it is incorrect, the reasons for there might be for them making these incorrect statements. Now, as scientists, of course, we have to confine ourselves absolutely to the interpretation of the data. It's for the sociologists to say why the conclusions our Japanese colleagues might have drawn particular conclusions. They did do so. Well, Mel Miles yesterday showed this slide of the cell, the ECOS. This is really the ECOS 1 or ECOS 2 type cells. And the important point here is there's a cathode in here, and there are two temperature sensors, and there's a palladium cathode. I'll return to this in a minute. And I have two data sets, one gathered by, I've cut out one of the data sets collected by Mel Miles in Japan. I have two data sets. One is the palladium boron system, which he talked about yesterday, and one is a particular data set collected by our Japanese colleagues using a material made by Tanaka Metals. And here is the temperature, time, and cell potential time curve observed during one measurement cycle. I'm sorry, the data points are rather large, so it looks as though there is more noise than there actually is. And superficially, this looks okay. We ought to be able to analyze this data set, and it is very much in accord with the instructions for the ECOS 1 and ECOS 2 systems. However, when we look at it closely, we see that actually, when we have the raw data, we see that it appears that our Japanese colleagues rewrote the software for the data acquisition computer, so that in fact the temperature measurements with the first and second thermistor are not correlated. That doesn't necessarily mean, it's not a disaster, but it means that the redundancy in the data is diminished, so it becomes somewhat more difficult to analyze the data. The much more serious point is that in order to be able to treat the data accurately, as I said yesterday, we can have an integral heat transfer coefficient. The easiest heat transfer coefficient we can evaluate is differential. We just take 3 adjacent data points because we have to get an expression for the temperature gradient with time, and therefore we have to, if we have a central difference, we have to 3 data points. So that's a differential heat transfer coefficient, but that's not a very accurate way of doing things. We should use an integral heat transfer coefficient, and the recommended procedure, ECOS procedure, is to integrate backwards, although our Japanese colleagues always insisted on integrating forwards. Now the disaster here is that, in fact, in rewriting the data acquisition software, the synchronization of the calibration pulse with the data acquisition time has been lost. I think you can see this by just putting a straight edge through the heating cycle, and you see that this just about hits the midpoint, so this is just about as bad as it can be, and means that we cannot, in any straightforward way, evaluate the integral heat transfer coefficient. We are reduced, in fact, to evaluating the differential heat transfer coefficient. Well, that's an example of case study. If they evaluated the integral heat transfer coefficient going forwards, which was not recommended, using an offset in the heating pulse, they would have got peculiar results. So we know by applying the case study methodology that we can't do that. We have to use the differential heat transfer coefficient at these particular points. Well, if we do that, this is done at low current density. The cell count was 0.2 amps, and we dominantly used 0.2 amps and 0.5 amps. And look at the heat transfer coefficient, we see the next disaster looming. And that is that the heat transfer, if we assume the simplest assumption we can make, there is no excess enthalpy generation. And here, lo and behold, we see that the heat transfer coefficient at 0.2 of an amp is different to the heat transfer coefficient at 0.5 of an amp. But if that is so, then of course we might as well pack up and throw this thing away. And associated with this is another observation, and that is that if we apply the heating cycle, the heat transfer coefficient is, and some of the heats delivered to the cell, some of them aren't. The heat delivered to the cell is the heat transfer coefficient is different when we apply the heating cycle to when the heating cycle is off. Now, I think the explanation for all this is quite prosaic. I should also make a point that our Japanese colleague said that this lower bound heat transfer coefficient, based on the assumption of zero excess entropy reduction, is bigger than the heat transfer coefficient which you observe by applying a calibration pulse, which is obviously not possible. As I said, the explanation for these effects, I think, is quite prosaic. There are actually two explanations for it, but this, I think, the root cause of it is quite simple, and that is that in the ICCCF-8 system, the whole thing was wired up with the leads, and the data acquisition points were at the cell. So this data acquisition was carried out with two four-terminal arrangements. This led to a great mess of wires, and I actually wanted to reduce this eventually to Kamak crate type data processing strategy. And what we did was to interpose switching boxes with heavy gauge external leads. Because now the data acquisition points were within the switching box, so this would only work, of course, with a heavy gauge wire. Now, in fact, as far as I can see, the experiment was carried out with the wires used for the ICCCF-8 system, but the data acquisition points were shifted to the switching box. Now, that, of course, means that you have a power input external to the cell, and you will get complete nonsense in the low bound heat transfer coefficient. I became aware of this possibility in 1995 and took the precaution to measure the resistances of these leads. And these resistances lay between 0.5 and 1.5 ohms. The only thing I can do now, not knowing what resistance they actually had in series, is to assume a median value of 1 ohm. And if I do that, then lo and behold, and equally for the heat leads in the calibration heater, then these data begin to collapse on top of each other. This scale is vastly bigger than the scale of the previous figure, and now the heat transfer coefficient for the measurements carried out at high current density are below those. The low current density before they were inverted, so obviously we have chosen too high resistance value. I don't think there is any justification for fiddling about with this. We just have to accept the data as they stand. So this actually is a 5% error. What they introduced is a 5% error. The experiment should be correct to 0.01%. It's now correct to 5%. Okay. Well, everything stays in order. The heat transfer coefficient is, if we go back and use the uncorrected data, we will get the same heat, we get essentially the same heat transfer coefficient all the way up to close to this is the penultimate day, and on the penultimate day, as Mallove said yesterday, we have to know the atmospheric pressure, in order to correct for the enthalpy taken out in the gas stream. And here is the calculation for the penultimate day done with 0.975, 1, and 1.025 atmospheres. So clearly, if you go close to the boiling point, we have to know the atmospheric pressure. Now, as far as I can tell, there was an online pressure sensor, but this was disconnected, so we do not know the pressure. However, we know that this is unphysical here. This is also unphysical, and we know that the pressure must have been in this range because we have to assume a pressure of this magnitude to explain the evaporation to dryness on the last day of operation of the cell. So we see that there is actually a significant drop in the heat transfer coefficient during this time, which means that there is a build-up of excess enthalpy generation, and this build-up of excess enthalpy generation becomes quite marked towards the end of the penultimate day. All right, then. So we come to the last day of operation, and on that day, after about 23,700 seconds, the cell wall is dry, and the cell begins to cool down. So we want to evaluate. One of the main things we can do is to say, well, let's evaluate the excess heat released during the last day, because we know how much heat we put in, we know how much heat goes through the walls, we know how much heat we require to heat up the cell contents, so we know how much heat we require to evaporate the cell contents. And we can do a thermal balance. And then we see that if they had in the system the prescribed number of moles of D2O, they would have had to generate uniformly over the last day an excess energy of about 1.622 watts. And that, of course, translates here to about 10% of the input enthalpy. But in fact, it's quite clear that they overfill the cells with electrolyte, and consequently, there were more nearly, you can get this by evaluating the water equivalent of the cell. They had more nearly 6 moles in it, and actually had about 3.38 watts excess enthalpy. Now that is an extremely easy calculation to do. By contrast, it is really rather difficult to get the distribution of heat, the time distribution of heat in that last day. Because you have to interpret this in terms of the colligative properties of solutions. Now that was a topic popular at the beginning of this last century, is now unpopular, but it's in all the physical chemistry books, and we have to have all this information. Now I have been quite unable to work out any scheme under which I could get evaporation requirements of the cell, of this particular cell. And I think the real reason for that is that the concentration is incorrect. If the concentration had in fact been higher, the limiting solubility would have been reached sooner, and we would have had evaporation requirements. And here I say that it is no use people saying that they did not see any excess enthalpy generation during this period, unless they give full details of how they attempted that interpretation. So we can't actually, because we can't get a full interpretation, we have to really limit ourselves to the beginning of this plot to calculate the excess enthalpy. The next thing our Japanese colleagues said was that they could not, there was no heat after death. But in fact, the simplest calorimetric experiment anybody can do is to measure a cooling curve of a cell. There is nothing more, but it's done by everybody in high school, and it's extremely simple. And if you eyeball these data, you see that this, you cannot possibly explain such a cooling curve by the natural cooling of the cell. There has to be a source of heat in the system. And if you look at the magnitude of the source of heat, I'll skip a bit here. You can see from the initial period of operation of the cell during this last day, you can see that if there is a constant rate of heat release, how it varies with atmospheric pressure. The true value is probably in here somewhere, and here is the heat release during this episode of heat after death. And if you have some faith in it, this point and this point will come together. Now 5 watts does not seem to be a great deal, but the lectern was only 0.04 of a cubic centimeter. So I would point out to you here that this heat after death is actually of the order of 100 watts per cubic centimeter. which is comparable to the heat released in the PWR, pressurized water reactor. And in fact, this is 300 seconds, this is 600 seconds. There is a massive heat release here. And of course, this heat release, if you just consider this part portion of the curve, this heat release is the efficiency for this heat release is 50%. So we were told that they had no heat after death, but in fact there is heat after death. Now I'll just point out one more thing. Otherwise, I'm running out of time here, but I shall be ruthless. I shall just point out this particular episode of Mel Miles's data. He pointed out that the shape of this curve showed that there had to be positive feedback. Applying the heating pulse actually leads to an increase in the excess enthalpy generation. And that is in fact so. Skipping madly through these slides, if you do the analysis properly, you see that there is in fact an excess enthalpy generation during the heating pulse, and there is zero excess enthalpy generation before the primary heating pulse. The palladium-boron system is extremely strange. It leads to positive feedback at an early time, and then you switch the heating pulse on, and the excess heat goes up. You switch the heating pulse off, the excess heat comes down. Now this system also shows heat after death. I haven't time to go into that, except perhaps to say that in this particular system, the heat after death was probably about 200 watts per cubic centimeter. And the real task which confronted us post-1992 was to integrate the operation of the cell in the periods of heat after death with the operation of the cell during polarization. Unfortunately, this hasn't taken place, so we have denied ourselves the means of making an energy-efficient system. With that, I shall leave you.